Hey everyone, I'm Brian Geisel, and we're talking about why synthetic data is better than reality. So we're starting the talk here, better than reality, supercharged autonomy with synthetic data in the whatever stage this is called. Just head towards the sound of the noise. All right, so the first thing I want to give is my 1 minute on what machine learning is. If you already know machine learning, it's only 1 minute. If you're new, this will give you a context of why we're talking about synthetic data. So, pre-machine learning, we look at traditional code. Traditional code is if-then-else kind of stuff. We're running loops, it's deterministic. Whatever I decided we're going to do, it's definitely going to do that. You've seen flowcharts. What happens in this situation? In this situation, we take this action. If this doesn't happen and this happens and that other thing happens, then we make some decision from it. That's what we get from traditional code. That's what we're kind of used to. It's how we think. With machine learning, it works differently than that. Machine learning, there is an algorithm side, but also we're using a lot of data. And that data, we call it training data, that training data has an awful lot to do with the decisions we make. And the decisions that we make are probabilistic. And so it isn't like the if-then-else traditional code method where if we're in this situation, exactly this thing is going to happen. So if we want to train a machine learning, a computer vision algorithm, for example, to recognize hot dogs, then we need lots and lots of images of hot dogs, and we need Timmy to circle all of the hot dogs. So we're going to take 100,000 pictures of hot dogs and of not hot dogs, and we're going to ask Timmy to circle hot dog or not hot dog in every one of these images. Timmy's had better days. Timmy's had better jobs. Timmy is not happy. And what we've been finding as we're talking to customers is that the amount of time that it takes to obtain their data, so that is someone going out and taking pictures of 100,000 hot dogs or whatever it is that we're training our data on, that labeling that data is taking at least as long. So if it takes us a year to gather 300,000 images of the thing we want to train on, it's taking us another year to label that data. We've heard all sorts of issues from, trying to use AI to do the labeling to speed it up, and then sometimes it's just wrong, and incorrectly labeled data is worse than unlabeled data. And so one of the nice things about Symage, which we'll talk about a little bit, and our booth is just behind here if you guys want to check it out at some point, but is that the images with synthetic data come fully labeled. And so there's no additional time for labeling those images. So reality, there are problems with reality. I don't know if you knew that before you came to this talk or not, but here you are, and now you know. There are issues with reality. So one of the things with getting training data is if you don't have access to the environment. If you want to get training data for the desert, and you're not in a desert, that's a problem. Scarcity, sometimes there just isn't enough of it. They run into things like folks that are, let's say the model's having trouble with shadows, and you just need more images of that specific thing, more images of things that have shadows because the shadows are confusing the model, or occlusion is, or all those kinds of things. Or 3D data is you buy an expensive LiDAR and then you get kind of okay data and it's not good enough for training on. So when you're training a model, remember those, if we're talking about a computer vision model, those images or those videos, a chef is only good as his ingredients. So if we're here training on Rotten Tomatoes, then we're not going to be as good if what we're trying to do is healthy tomatoes. So before I dive too far into the this piece of synthetic data, I do want to separate. There are different kinds of synthetic data. So one thing that's been done for a long time is time series data, or sort of records data. So you want to see if your database would handle 1 million database records, and so you create records-based synthetic data. That's been around for a long time. It's a pretty mature market. What's pretty new is image and video data. And so that's what we're focused on and looking at. Specifically what we're talking about in this talk today is image and video based data, which is a little different than some of the other kinds of synthetic data. So there are a few different ways that we can go about creating this data. So one is using generative adversarial networks. And so here we have this generator and a discriminator. So the discriminator, let's say, is good at recognizing human faces. We can show it an image, we say, is this a human face? And it's pretty good at saying yes or no. We use this generator and it starts generating random data. And over time it trains and it learns to generate data that the discriminator says, yes, that looks like a human face. And so it's lots of images that you might get from a machine learning site today, an AI site that's generating images, will be something generated by a GAN. This image is from one of my favorite websites, thispersondoesnotexist.com. And this person, in fact, does not exist. This is a generated image from the previous methodology, so generated from a GAN. But one thing that's really interesting is that the discriminator that's saying this is or isn't a person doesn't care what's happening in the background. There's brick behind him, and we all kind of just look at the face. But if you look at the brick, what sort of brick is wavy? And what sort of brick is set up in these other sort of weird patterns? It sort of looks like brick, but not really brick. It's not really cohesive. But the discriminator doesn't care about that. It cares if this is a face. So one of the other things that's an artifact that happens here all the time is if a woman's wearing an earring, the other earring will always be different. Now, that's not what you would normally see in the world, but if you looked at a woman with 2 different earrings, would you go, well, that's not a person anymore? No. So it says, yep, that's a person, and the side of it that's training on what is this starts having these artifacts that aren't bad enough for you to say it's not a person, but probably aren't what you're going to see in the real world. Another way that we can create is from diffusion. And so with diffusion, you're gradually adding noise and you're learning to reverse the process. It produces high quality diverse images. One of the negatives is it has artifacts. So you can see in this image that was created through diffusion, the left side where it says real data, that worked pretty well. The right side sort of says generated data, but doesn't quite. And so again, there's some of these little details and inconsistencies that become a problem with some of these when you go to train on these. Variational autoencoders, VAEs, is another method. Some of the other things you could be doing is like, there's a couple examples here where you can do procedural things where you just invert an image, you mirror an image, you flip it, these kinds of things. Or procedural generation. So this is generally a good way to generate sand. I can use random data in shades of brown and tan, and I can generate it in these patterns but not these patterns. So you can actually come up with some interesting things where you generate things procedurally. Certain things in video games will use these kinds of things. So let's talk for a minute on the other side then, the kinds of training problems that people are running into. So one of the things that we ran into someone with was they're training in the kitchen. And so they've got toasters in the kitchen. Makes perfect sense for a model to see a toaster in the kitchen, sees lots of toasters in lots of kitchens, really good at recognizing a toaster in the kitchen. They said that even really good at recognizing a cell phone, which may or may not be in the kitchen. May have forgotten it in the kitchen when I went out wherever it was that I now don't have my cell phone. But one thing they had a problem with was occlusion. So if this toaster is hidden by my cell phone, or my cell phone is partially blocked by the toaster, then they weren't recognizing it. So to do that, you pull in more images of those things, the things that you have a deficiency in. So this is one of the great places where synthetic data comes in. Another place is if you're training your model to recognize depth. So if one of the important things to your model is understanding how far away an object is from you, then you need really good depth information as well. So the interesting thing is, in the real world, our depth is a little fuzzy. We can use LiDAR, we can use different things to try to get a depth. With synthetic data, and so the way that we're looking at is scene-based or simulation-based synthetic data. So with that, one of the things is interesting is the depth-based data is math. So you can have it as precise as you want to have it, because it can actually be perfectly precise because it's just based on math. And as I mentioned, one of the issues folks are running into is the labels on the data, because it's very important to have labeled data. If you're generating it and you're using AI to label it, or you have people labeling it, and you're like, oh yeah, this is an ugly dog. You and I know this is not an ugly dog. It's a giraffe. But with synthetic data, I can get the depth of every point on this giraffe. I can get all sorts of other information about what's happening. If the giraffe's behind some grass, I can know exactly where the grass is and grass ends, where the leg starts, even if I can't see the leg, right? So these are the kinds of things that all of a sudden you can bring into training your algorithm on. Then the other thing is, you don't have enough of the object. You don't have enough angles. You don't have enough lighting, all those kinds of things. And so with synthetic data, you can generate all sorts of different angles, all sorts of things that we as humans, because we're sort of, if you think about it this way, we're sort of in a video world. Like, we don't really see still images. We see how they relate one image to the next image. We see angles around things all the time, right? As I walk back and forth across stage, you've got a 3D map of my face. Also, it helps that you have two eyes. But you're getting that 3D information. You're getting context information about how I move or how I walk, all these kinds of things. And so very often the ML that we're training is missing that data because we have one image of an object, or we're taking all of our images from the same spot, because it's just, we need lots and lots of data. It's just faster and easier to take them from the same angles, these kinds of things. But with synthetic data, very easy to mix up the differences in angles, in lighting, all sorts of things along those paths. And then the other thing that I think is very interesting is multimodal. And we're just starting to see folks training some things on multimodal. If I were to throw something on the ground, take a glass and smack it on the ground and it exploded, you would inherently associate the loud crash you heard with the idiotic thing I did. But that's because we process those together. We hear the sound, we see the visual. You don't necessarily get that as you're training an algorithm. And so being able to process things multimodal so that your AI can have that, and I know we don't like words like comprehension or understanding. We anthropomorphize all the time. But for the sake of common language, for your ML to understand those kinds of things, you need to feed in that multimodal data. And so, okay, audio, visual, that's interesting, it makes sense. What about smells? And I think smells is one we go, whoa, they've been trying to get smells into theaters. Like, I've never been to a movie theater where you can smell the movie. It's crazy, it doesn't work very well. Yeah, that's the output. This is input side. And we're actually pretty good at that. We have plenty of sensors, CBRN, right, that detect chemical, radiological, nuclear, all kinds of different things that we can sense. So sense those, bring those into the model that you're training, especially when we're talking about autonomous robotics. And so you want your robot to be able to navigate and maybe map out nuclear radiation and understand where it is. So you have a sensor for that, that's fine. But if you've got a model that's autonomously navigating, you might be able to use that data as well as visual data, as well as audio data to process and to navigate the way that you're doing it. And so the thing that that we found all of a sudden customers were coming to us for, and we're like, oh, hey, look, there's a product here, there's a need here in the market, is doing simulation or scene-based synthetic data, which solves so many of these different problems around, having perfect depth, being able to generate exactly what it is that the model's missing. And so we had a situation where NASA came to us and they said, hey, we would like to be able to navigate a vehicle on Mars. And, so there's rovers running around on Mars today. And they said, we'd like to be able to navigate a vehicle that can go, say, 2 kilometers to the edge of this crater. That's fine. Waypoint the robot, right? We know how to do those sorts of things today. Because teleop on Mars, kind of a pain in the butt. At furthest distance from Earth, it's 22 minutes for the speed of light to reach Mars and back. So it's about 45 minutes for me to send a command, move the robot, get some data back to see if I ran into a rock or not, and then repeat. So it's a pretty slow way to move on Mars, but we do want to see what we're finding as we go. And there's all sorts of restrictions, right? The bandwidth, the speed at which we can get data back from the rovers, all this kinds of things. And so NASA said, listen, could you guys help us identify blueberries on Mars? Okay, blueberries on Mars are like grape nuts on Earth. They ain't grape and they ain't nuts. So blueberries on Mars, they're not berry, and they're freaking not even blue. So they're these spheres, hematite spheres, so they're high in iron, they're kind of grayish in color, maybe a little reddish, and NASA thinks that there's a good chance that they formed an aqueous chemistry. So there may have been water that was sitting or flowing in these places at one point. So it's a good place for us to look for signs of life on Mars. So when I say we're looking for life on Mars, I don't mean like little green men, but I don't think it would hurt if the model could recognize those too, just in case, right? We don't want to be looking for bacteria and some guy's looking in the camera and we missed that one. I'm just saying. So all the training data that NASA had for this already was none, because it's freaking Mars. So there's no training data whatsoever. So they said, look, can you generate training data for us so that we train a model and then run it on a rover on Mars? So we say, look, go 2 clicks over here. We want you at the edge of this crater. We don't want to have to teleop the thing. You go and just stop and tell us if on the way you found something we deem could be a potential sign of life. So use these blueberries as a potential kind of initial starting point. So as you can imagine, there are a bunch of issues with generating training data for Mars. And so you can't just go check it. You can't just go fix it if it's broken. You can't tip the robot back up. There's all sorts of, we've got limited bandwidth. When the network's there, it's probably broken. It's all kinds of these sorts of things that are an issue for doing this on Mars. So what we did in order to generate good synthetic data for NASA was, first, we have some images from Mars. We have a lot of images from Mars, actually. So that's good. So we took the images that we have from Mars, and then we have high resolution scans of things like rocks here on Earth. We have plenty of those. Take the ones that most resemble Martian geology. And so take the ones that fit the kind of makeup and the sizes and the structures and all this that we have on Mars, and then create a simulation from that so that it resembles what we're going to find on Mars it's photorealistic, this kind of thing. But then we've got the issue that Mars has a different atmosphere. It's a different distance from the sun. It's got things like lots of iron on the surface, so that's where you get this reddish hue. Those all change the way that we're going to see things, or the things that the camera is going to pull in on Mars are going to be different than Earth. And so we've got to do things like adjusting for the atmosphere, adding noise, shifting color, all these kinds of things that make it what the image is actually going to look like on Mars. So we're training on data that's going to be pretty representative of what the robot's going to look like on Mars. So the interesting thing about synthetic data that's really cool is you take this original object, and if I took a real image and I'm circling the hot dog, that's fine, but annoying, slow. I've got a data scientist probably circling hot dogs instead of doing data science. So one of the cool things about the product that we built was that the instances are automatically labeled. So we can do instance label and semantic segmentation. So here, for one time in the life of these blueberries, we have made them blue. So just this once, they get to be blue. So the segmentation there on the right is, these are the things of interest to you. But depending on how your model's set up, you might want the one in the middle as well, or instead, which is just, here is what every single thing in this image is, so that you know what you're looking at. And one of the other things that we set up in this process was a way to basically hot swap the real world for the robot. And so this giraffe framework that we built that makes use of the simulation, the synthetic data that we're pulling in, it uses things that exist today, right? You build your robot code in ROS or whatever you're building in, that's totally fine. And then you are going to do a simulation in Unity, or you're going to do it in Unreal Engine, or you're going to do it in Gazebo, whatever that is, whatever works for you. What we did is, instead of having to simulate the robot in MATLAB, something like that, where you set up the entire process of doing the simulation, and then you go, okay, we proved it works, let's throw it away and write a bunch of code in ROS that works on the actual robot now. Write your code, however you're going to write your code and deploy it in the first place. You put that through the giraffe framework, and essentially what we can do is hot swap the real world on the robot. So we can take a sensor that was a camera, and instead of feeding you the camera, we feed you a camera from Unreal Engine, or from Unity, or from Gazebo, et cetera, et cetera, et cetera. And we, instead of using your CBurn sensor, you need to do radiation detection. So we give you radiation detection inside the simulator. And now your robot can run and do the things it needs to do its autonomy, whatever it is, within the simulator. It lets us also do a couple of interesting things on top of this, which are, you can inject errors. You can inject, so one of the things we have trouble with in space is the network's pretty crappy, so you never know when it's going to go out, what your bandwidth's going to be like, this kind of thing. So we can simulate those kinds of things. We can simulate the edge cases, because that's where we get hung up in this stuff, is straight line, it works great, but what happens in the unexpected? So we're able to simulate those things. The other thing that I think we get caught in sometimes in the robotic world is we have a simulator, which is just all the compute power in the world. And then say we're doing drones, they have limited compute. But in the simulation, it worked great because we had unlimited compute and we didn't care who was computing. We just said, do this, run the drones around, and look, everything worked fine. One of the other things that's nice about Giraffe is you can bring the processor you're actually going to use, say on the drone or on the UGV or whatever it is. You can use the actual processor that you're going to use. You can give the actual compute workload on that processor. And again, it's just sort of like, if you remember the movie Inception, Like it's like Inception for robots. It doesn't know it's not in the real world. And then when you want to run in the real world, turn off the simulation, give it a real camera. Turn off the simulation of nuclear radiation, give it a real nuclear sensor. And then you may or may not be running it with real physical hardware that you're running your compute workloads on. So you can run it that way. And that gives you this ability to train on what you're actually going to use your actual code, not have to swap your code in and out for the thing that you're actually going to real world deploy, whether that world is Earth or Mars. So I'm happy to take some questions. If this was helpful to you, which I hope it was, there are a bazillion ways to contact me. If that's interesting and you'd like to follow me, just so y'all know, this is what I look like from the back. All right, any questions? We got a couple minutes. I can take a few questions if we have any. Yeah. And here, hold on 1 second. We got to, yeah, perfect.
So for custom sensors like CBurn sensors, how are you characterizing that when your customer comes to you and has like, I have sensor A from this brand versus sensor B from this brand? Is that custom to everyone?
Yeah, so great question. So it definitely depends on the sensor, and it depends on how much you care about the data from that particular sensor. So if you, like, the first thing that a lot of folks will probably do in simulation is work with perfect data first, right? So we can simulate perfect and give you exactly what the right answer is first, and then start backing you down. And that's where, yeah, if you're going, I want to use this sensor, then we have to model that particular sensor and go, okay, where are the deficiencies, or what's the drift we get, or whatever that is for a particular sensor. So yeah, at that point you kind of get custom to that sensor. The other nice thing is you can run in the simulated world, but if you have a real robot that's running out in the world, you can run the real sensor on it also, and you can also intercept that and then insert errors on top of whatever the imperfections are from the real sensor.
Are there medical device training applications for this? And then what would you simulate in that case?
Yeah, so we aren't today, but it's definitely something that we're looking at on the roadmap, is things like MRIs or even things in the body. In that sense, it's interesting because you've got like this scene on Mars, but if you think about it, the human body or something I'm getting from a microscope or whatever, it's similar. It's still a scene. It's just a different magnification or scope that I have on a scene. And so there are some things where, so for example, for an MRI machine, one of the things that's kind of easy to do programmatically is get lots of angles and lots of lighting and this kind of thing. So we talked to somebody with an MRI. We're like, oh, how many angles do you have? Kind of knowing what maybe the answer was. And they were like, yeah, there's one angle. Because our goal is to position the thing that we need to run the MRI on perfectly under the sensor, and you're just going to get this top view or however that works. So there are some things where you wouldn't get mileage necessarily out of changing the angle for MRI, because what your model is going to end up looking at is going to be pretty similar each time. But then things that you can model off of that are whatever it is that I'm going to look at in an MRI is, okay, I have lots of images of this situation, whether it's, I don't know, broken leg or something happening in the brain, and then you can make changes to that where you go, okay, this you don't see enough of. This is the stuff that will create as synthetic data. So, but it's not as clear as the stuff that we sort of see in the world around us, which is why it's one that we haven't tackled yet that way. Yeah, other questions? Quick, we got 30 seconds. All right, perfect. So I'll be around, and our booth is actually conveniently located right behind here. So if you'd like to stop over and talk to us, we'd be happy to chat with you. So thanks so much for joining.